We're covering volumes by cylindrical shells and the average value of a function. Let's start with volumes by cylindrical shells. So recall that so far we can calculate the volume of a three-dimensional object using the disk washer method. However, there's a problem because the disk washer method may not work in some instances, and I want you to consider the below example. So here's the example. I want you to use the disk and washer method and try and calculate the volume obtained by rotating the region bounded by the x-axis and y is equal to sine x, and you're rotating this region about the y-axis. So here's the region. I've shaded it in blue. It's between sine of x and the x-axis, and what we're going to do is we're going to rotate it. We're going to rotate it about the y-axis. So take a minute, use the disk and washer rules that you learned, and try and find what this volume is and check if you encounter a problem along the way. So let's do this. We are rotating it about the y-axis. The y-axis equation is x is equal to 0. So according to the disk and washer rules, I'm rotating it about x is equal to 0 and x is equal to something line. So I need to be integrating with respect to y. My cross-sectional area is going to be in terms of y. Now let's take a closer look at what happens when I actually rotate this figure. So if I rotate this figure, firstly, this portion is going to be rotated. And then the outer portion is also going to be rotated. So it's going to look, the three-dimensional object is going to look kind of like a washer. So we're going to have an inner radius and we're going to have an outer radius. Okay, so my cross-sectional area is going to be in the form pi r2 squared, where r2 is my outer radius, minus pi r1 squared, where r1 is my inner radius. So r1 is the blue line. So let me label it. Here's r1, that's r1, and this is r2, those straight lines. Now, let's take a look at what these radii are. If we take a look at r2, the outer radius, it's the distance from the y-axis to a point on the curve, and that is just an x value. The same applies for r1. We have a distance from the y-axis to a point on the curve, so that again is just an x value. But remember, my cross-section, so this is going to become pi x squared, where this is the x value for the outer radius, minus pi, and let's just write x2, so you don't get confused, and minus pi x1 squared, where x1 is the x distance for the inner radius. So x1, x2. But my cross-sectional area needs to be in terms of y. So how do we convert from x to y? We are going to use our function equation. So we have y is equal to sine x. So we need to solve for x. That means that x is equal to arc sine y. Now I'm going to pause here for a minute because I see that I'm going to have to substitute arc sine y in place of r, and then I'm going to have to integrate that. That immediately sets off alarm bells because yes, while I can integrate arc sine y, it's going to be very difficult. It's going to be difficult. There may be an easier way to handle this entire example, but let's continue through and see where the problem actually lies. So this means that x2 is going to be arc sine y because it lies on this function. But it also means that x1 is also going to be arc sine of y, okay, because it lies again on the same function. Now let's take a look at what happens when I substitute these in place of x2 and x1. It's going to be pi into arc sine y, and that arc sine y squared, minus pi of arc sine y, and that's going to be squared. Now these quantities, take a look, are the same. So this is telling me my cross-sectional area should be 0. And we can see intuitively, if we had to rotate this entire region, okay, about the y-axis, that the cross-sectional area is not going to be 0. The reason why we kind of get a 0 here is because these x values, they lie on the same function, or they apply to the same function. So obviously this is incorrect, and here is where the problem lies. So that is why we have to use volumes by cylindrical shells in order to solve this problem. So let's go and look at the rules or the methodology for the volumes by cylindrical shells. All right, so here are the rules for volumes by cylindrical shells. So to calculate the volume in the above example that we looked at, we use the method of cylindrical shells, and the general guideline of the method is given below. So we are going to have two cases, just like we had for the disc and washer method. Okay, and it all revolves around what line we are rotating about. Are we rotating about an x is equal to something line, or are we rotating it about a y is equal to something line? Just like how we had the two cases in disc and washer method, we have two cases here. Let's cover case one. We are rotating a function about the line x is equal to a. So x is equal to something. Here are the rules. You're going to use dx, so you're going to integrate with respect to x. Then, if the figure lies to the left of the line x is equal to a, so when I say x is equal to a, that's your axis of rotation, basically, the line you're rotating about. If the figure lies to the left of the line x is equal to a, you're going to set a variable r, and r is going to be a minus x. R is a variable that you're going to use in your integration. Don't worry too much about what it means. Just use it in the formula. Uh, you can think about this as kind of the radius, all right? That's why the variable r. So you're going to set r to be a minus x if the figure lies to the left. If the figure lies to the right of the line x is equal to a, then you're going to set r to be equal to x minus a. Okay, so that's basically the first major step apart from using dx. Then your height is given in terms of x, obviously, because you're again integrating with respect to x. The height is given by the height of a rectangle drawn anywhere in the shaded region, and the rectangle is drawn as follows. So the rectangle is going to look like a very tall skyscraper. And just a note, you don't really have to draw a rectangle. You can even just draw a vertical line to figure out the height. I just use a rectangle because in many textbooks, the volume by cylindrical shells, they're typically explained using rectangles that kind of create a shell figure. Again, you don't need to draw a rectangle. You can just draw a vertical line, right? So the height is going to be given in terms of x. I'll show you how to do that in an example. So once you have your r as well as your height, it's super simple. Your volume is given by this equation. So 2 pi multiplied by the integral from a to b, and a to b are obviously x values. Those are your bounds of integration. And then you're going to multiply your r that you got by the height of this rectangle, and then again integrate with respect to x. That's how simple it is. All right, let's go on to case 2. So case 2 is where we rotate a function about the line y is equal to a. So now we're doing about y is equal to something. Surprise, surprise, we are going to use dy. So we're going to integrate with respect to y. Now, again, if I'm rotating, so let's take a Cartesian plane and let's say here's my axis of rotation. The figure is no longer going to lie on the right or the left of this line. It's either going to lie above here or below the line. So that's why we have above and below and not left and right, like when we were doing x is equal to something. So if the figure lies above the line y is equal to a, you're going to set your r, your radius basically, to be equal to y minus a. If the figure lies below the line y is equal to a, you'll set r equal to a minus y. Next, your height is given in terms of y, and it's not really a height in this case, but for consistency, I'll show you what I mean. So the height is going to be given in terms of y. The height is given by the height of a rectangle drawn anywhere in the shaded region, and the rectangle is drawn as follows. So it's a skyscraper, but this time it's fallen down. So it's on its side. Again, if you want, you can draw a horizontal line to represent the height. Okay, so either one of these is perfectly fine. Again, I used a rectangle because that's how it's explained in a lot of textbooks. So just remember that the rectangle needs to be on its side if you're rotating about the line y is equal to a, or a horizontal line. Then it's super simple. Just substitute everything in the formula. The volume is equal to 2 pi of the integral c to d. C and d are now y values. Those are your bounds of integration. And again, multiply your r by your height and then integrate with respect to y. Just one more thing that I want to point out in case you're having trouble memorizing this and memorizing this. Is it x minus a? Is it a minus x, y minus a minus y? This is what I want you to remember. So if the figure lies above the axis of rotation, or if it lies to the right of the axis of rotation, so above and to the right, then if it's to the right, it's going to be your variable x minus a. If it lies above, it's going to be your variable, which is y. Again, we are integrating with respect to y minus a. So if it's above or it's to the right, it's always variable minus whatever you're rotating it about. That's how I want you to remember it. Okay, and then if you have left and below, you'll know that it's a minus your variable. So let's take a look and prove that this actually works. If it lies to the right of the line, it's variable minus a. Then if it lies, where is above? If it lies above the line, it's variable minus a. That's what I want you to remember. So you don't have to memorize four things, just remember two. So let's go into an example and see how this is done. All right, exercise 1. Calculate the volume obtained by rotating the region bounded by the curve, and here's your curve, minus x squared plus x, and the x-axis about the line x is equal to 0. So here I've given you your region, and we are rotating it about the y-axis, that's x is equal to 0. So we are going to use the volume by cylindrical shells method. So if you want to try this on your own, pause the video now. So we're rotating it about the line x is equal to 0. That means we need to be using dx. Now, here is the line of rotation. I'm going to highlight it in blue. Does the figure or the area lie on the left or on the right? Okay, so here's the figure, that shaded blue region. It clearly lies on the right. So we are going to set r to be equal to, remember when it lies above or to the right, we are going to have variable minus 0. Our variable is x, so it's going to be x minus, and I said minus 0, not minus 0, minus a in general, but I said that because here we have the line, x is equal to 0, so a is 0, so it's going to be x minus 0, and that's going to be x. So r is going to be equal to x. Now let's go for the height. So the height is going to be given in terms of x, and because again we are rotating it about a line x is equal to something, we need to draw the rectangle vertically. So it's going to look like a proper skyscraper. There we go. Okay, and now we need the height of this rectangle. So the height of this rectangle is the distance from the x-axis to a point on the curve. And that's why I sometimes find it more useful to in fact just draw a line instead of a rectangle, because you could get a bit confused with the rectangle and think, okay, where's the height? But if you just draw a vertical line, you can see the height of this vertical line quite easily. So let's stick with this vertical line. What is the height of this vertical line? Well, that's the distance from the x-axis to a point on the curve. That's nothing but a y value. But remember, we are integrating with respect to x. So we need to convert from y to x. How do I do that? I'm going to use my function equation. So this y is going to be minus x squared plus x. There we have it. There's your height. Now all that's left to do is put this in your integral. So your volume, I'm going to write v for volume, is equal to 2 pi into, and let's identify our bounds. Our bounds are going to be in terms of x, and this figure starts at x is equal to 0, going to x is equal to 1. So from 0 to positive 1. That's how easy it is to identify your bounds. Then it's going to be r times by your height. R is x, so it's going to be x into, what's your height? Here's it here, minus x squared plus x. And then we integrate with respect to x, and that's it. That's how you set up your integral. All that's left to do now is integrate. This will simplify to 2 pi 0 to 1 minus x cubed plus x squared. This is super simple to integrate. Once you integrate it, your final answer will be pi over 6 units cubed, right? Because again, it's a volume, so units cubed. And that's how you use the cylindrical shell method.